students, Dr. Stragi here. We're moving forward in our unit about statistics to talk about ways that we measure what we're calling the central tendency of data. What we're headed for here is something like mean, and then later ways of estimating the mean, like average and so on. But I want to tie this back to what we saw in the last lecture, where we were talking about the difference between statistics and parameters. I mean, remember, a parameter is something that it's a real thing. It's a property of a system. It is the mean amount of power on the electrical grid, or the mean temperature, or whatever. But that doesn't necessarily it's not necessarily something we can actually know. Rather, we have to use statistics, numbers that we can calculate as a function of a sample of data, in order to compute things like the mean, or the median, or the mode, or the standard deviation, or whatever, as we'll be seeing over the course of this module. And we should be able to use this idea of our statistics to get a handle on what our, or at least put bounds on what our parameters, like our mean, are. And so when we're talking about central tendency, we should have some sense that there should be some kind of parameter that describes where does the system tend to cluster? What is the value of this random variable that we kind of seem to be aiming for, or whatever, the middle of it, if you will. We should be able to use our sample of our data to compute a statistic that is going to be able to make an estimator of what this central tendency of the random variable is. Now, when we come to actually trying to figure out what the parameter that we're trying to get a handle on is, our best bet is going to be mean. I've mentioned that I was a stats major as an undergrad, and I can tell you that there are other ways it can be done, but in the purposes of science and engineering and economics and all those kinds of fields, realistically the mean is almost always what we mean, no pun intended. But it turns out mean turns out to be a really hard term to define. It turns out to be a kind of term that you sort of have to know what we're talking about. I mean, this sort of center to the observations. If we could look at all the observations, where is the middle? Or we could look at the population, is perhaps a better way to think about it. If we could look at the population of all the possible observations, what's sort of this middle? Turns out mean is a really tricky term, though, to actually come up with a definition that we can all agree on. On the other hand, once we know what we're talking about, we all know what we mean by the mean. And the symbol for mean is a lowercase Greek letter mu. And so like if we have a random variable that we've decided to denote x, then like each of our observations of x are x1, x2, x3, all the way up to xn. And our notation for the mean of this random variable x will be mu x. Okay? Now, in general, there's no way to know the mean, right? We've talked about this a couple times now. There's a very large, if not infinite, population of possible, either existing or conceptual samples we could take. We could talk about like the mean power on the mean electrical load on the grid for a city. Well, that could be a very hard thing to get a handle on, because there's basically an infinite number of possible different times we could take the observation, conditions, possible growth in the city. I mean, it's just a very difficult thing to get a handle on. There really is such a thing as the mean electrical load on the grid. It's just that it's not something we can actually know. But we do have estimators of the mean that are ways that we can get a handle on what, at least we can put some bounds on what the mean could be, or we can make tests about the mean, like we can use a sample to determine the mean of the electrical load at this city is greater than the mean of the electrical load at that city, and so on, without actually knowing the mean itself. So if we're going to start thinking about estimators of the mean, well, obviously the elephant in the room is the average. Okay? Everybody knows about averages. In fact, in our day-to-day life, we tend to use the words average and mean as kind of synonymous. And statisticians even sometimes slip up and do that too. Strictly speaking, an average is a statistic. It's something that we compute based on the sample that we took. And the mean is a parameter. It is a property of the system. But even in stats textbooks, I catch it all the time, where there are places where they've used the terms interchangeably or so on. In fact, I caught myself as I was reviewing for this PowerPoint, where I had made a mistake on one of the slides where I wrote the word mean when I meant the word average. But I mean, because we tend to use these terms so very close. Strictly speaking, if you attach the word arithmetic to mean, the arithmetic mean is the average. That's one way that you could get around that problem. But we're going to be trying to use these words differently here. Now, the average is the simplest statistic you know how to compute. This is the add them up and divide by how many you got. Add them up and divide by n kind of statistic. Notice our notation here. We are saying that the notation for the average of a random variable x will be x bar. And all we do is we take the sum of the values of x across our sample from x1 up to xn. That's the notation here with that summation symbol. We're summing up x1, x2, x3 all the way up to xn, and then we're just dividing through by the sample size n. Simplest thing in the world. Here's the slide where I made a mistake. I said here the biggest issue with the mean is that it's highly susceptible to outliers. Nope, cross that out on your notes or whatever. It's the biggest issue with the average is that it's highly susceptible to outliers. What do I mean by outliers? I mean observations that are way outside the range that you were expecting. I know a classic example that is used at Creighton when they're teaching about statistics and they want to talk about outliers. Let's say you wanted to know something about the mean income in Omaha. Okay, so you're going to maybe sample 100 people, find out what their income is, and take the average of that. Okay, great. So you take 100 people, pull them out, and you've got some people with higher incomes, some people with lower incomes, but the average turns out to be an estimator of the mean. But what if one of the 100 people you pulled out happens to be Warren Buffett, who lives over there in Dundee? Yeah, his income is, billions of dollars, or at least his wealth is billions of dollars. How does that figure in, right? I mean, he's an outlier. You didn't mean to pick, no pun intended, but picking him doesn't help, right? And yet your average, gee, are you really going to say that you picked 100 people in Omaha and you took their average income and it worked out to like, I don't know, with Warren Buffett in there, let's say the average turns out to be $100 million. Are you really going to say the average income in Omaha, the mean income in Omaha, rather, is $100 million? No, that's not even a good estimate of the mean, right? I mean, mean income is, I don't know, probably pretty close to the national average, which is something like $40,000. Yeah, so he's an outlier. In the same way, you could maybe be taking the measure of the pressure, okay, to use a meteorological example. All right, you could take the measure of the pressure at your station at a large number of times and then take its average, and that would be an estimate of the mean pressure. But what if some of those days the pressure was ridiculously low, like maybe there was a landfalling hurricane? Okay, well that isn't representative of what's going on in general, that's an outlier. And if you have outlying values, whether they're legitimate or whether they're a mistake, like the data were entered wrong, the mean, again I have it wrong there, it's not the mean, it's the average that gets greatly disturbed. Now, let's actually do an example here. Alright, so here on those little colored blocks there, I've put in 13 observations that I just made up, of course, of the temperature right now around Omaha. They've got 13 different weather stations around the city, let's say, and I took observations, and oh, look, they're all about there, and we could take this n equals 13 observations, and we could say, right now, here, temperature in Omaha is going to be our random variable. We'll call it T. And I could take my 13 observations, add them up and divide by 13, and I get the average, T bar. And T bar is, what do I get there? 72.923 degrees Fahrenheit. Fantastic. Average. Okay. Now, here's the deal, though. Do we believe it? Because I happen to notice that one of these observations, the one I highlighted with a little black box there, it's an outlier. Instead of being like in the 70s like all the other observations, this observation has a temperature of like 47 degrees Fahrenheit. Like, what, more than 20 degrees cooler than any of the other ones. Maybe it's a mistake. Maybe it's real. Maybe right now, like there's a cold front approaching from the north, and that farthest north weather station in Omaha, the North Omaha weather station on 72nd Street maybe, is already getting it, and that's real. I don't know. Maybe it's a mistake. Maybe it's real. But no matter what, it's in there. Maybe I don't trust it. Okay, well, when I took the average based on the 13 observations that I did trust, I got 72.9 degrees Fahrenheit. But let's say I, for some reason, said, you know what, I don't trust this observation, it looks like a data error, somebody entered that, I bet it's supposed to be 74, I'm going to throw it out. Well, if I just take the 12 observations I trust, look at my new value of the average, T bar, 75, almost 75.1. See how just getting rid of one outlying observation moved my average quite a bit? That's kind of less than ideal. There's a technical term for this. We would say that the average is not very resistant because it is sensitive to just relatively small numbers of outliers. When we computed the average income in Omaha, when we included Warren Buffett, and we suddenly got this huge income, that's because the average wasn't very resistant to these outliers. All right. In the same way here, I moved the average temperature across the city by 3 degrees just by throwing one observation out. There's going to be good things and there's going to be bad things about averages, but one of the bad things about averages is that they are not very resistant as a measure of as an estimator anyway of the mean. I mean, there is some mean temperature in the city of Omaha. There is a mu-t at this present time. And we computed two different estimates of the mu-t just based on slightly different samples, and we got pretty different estimates. That's not so ideal. Well, let's look at other ways that we could have estimated the mean. And another common estimator of the mean is the median. Our symbol for median will be x, for like the median of a random variable x will be x with a tilde on top of it. And, the mathematical definition of median is a little awkward. I mean, the median of x is either, what you do is you sort the observations out from lowest to highest and you pick the middle one. Okay? So that half of the observations were greater than this and half of the observations are less than this. The mathematical goofiness here of this definition, basically if n is odd, you pick the middle observation so that there are just as many observations below you as there are above you. If n is even, you actually take the average of the two middle observations as a way of computing the median. Okay, so the basic idea of it's not so difficult, especially if we show an example. Okay, here again are those same 13 observations of the temperature right now in Omaha at different locations around the city. If I want to use the median as a type of estimate of this, what I'm going to do is I'm going to scramble these up so that they are now in order from the lowest observation, 47 degrees up at the top, down to the highest observation of 77 degrees down there at the bottom. So I just shuffled them around, and I'm going to pick the middle of them. There's 13 observations, so there should be 6 below and 6 above my observation, and I highlighted it there with a black box. It turns out that the median of these, T tilde, is 75 degrees Fahrenheit. Okay, and this T tilde is an estimator, anyway, of the mean mu-t. Okay, all right, that would be one way to do it. And this median turns out to be a whole lot more resistant to changes. It is resistant because it is less sensitive to relatively small numbers of outliers. I mean, take a look here. We computed the median of this data set as being about 75 degrees. Well, what would happen to the median if I had decided I don't trust that observation of 47 degrees Fahrenheit? That lowest one that seems 25 degrees lower than all the other ones can't be right. Let's throw that one out. What becomes the median then? Well, then the median is, of the 12 remaining observations, the median is just the average of the two middle ones, which both happen in this case to be 75 degrees Fahrenheit, so the median is now 75 degrees. Hey, wait! The median was 75 degrees before when I included that outlier as well. Nothing happened. It didn't change at all by throwing out that outlier. Oh, well that's pretty neat. Look how resistant that outlier didn't hurt anything in a median. What happens if that outlier is even worse? What if we decided that instead of 47 degrees, what if one of our observations around the city came in at 17 degrees? Okay, is it really 17 degrees at one of the weather stations in Omaha when every place else is in the 70s? Probably not. It's either a calibration error, or an instrumentation error, or data entry error, or who knows what. But you know what? It's in there. And if you want to go ahead and use it when you compute the median, okay, let's pick the median of these 13 observations, including that really gratuitous outlier. 6 observations above, 6 observations below, we end up with 75 again for our median. Once again, nothing changed when we added in this terrible, terrible outlier. The same would be true if we we're talking about mean income the median and income in Omaha. All right. If you picked 100 people and you let's pick a odd number, 101 people. Okay. Your 51st, you put them in order of their income. And the 51st person would be the median. And it wouldn't matter if you happened to, of your 101 people, to have picked Warren Buffett. Yeah, he'd be person number 1 with the most of income, or 101 I suppose if we ordered him that way. But it wouldn't matter. he would just be he'd just be the top one, but that isn't what we're looking at. We're looking at the median, the middle one. Now, my example where I did the temperatures in Omaha or I did the income in Omaha, I mean, they just both happen to be examples where the median was remarkably resistant to outliers. It turns out, depending on how many outliers there are and so on, you can make the median move a little bit based on outliers and so on. But in general, the median is a really resistant statistic. It really resists the role of outliers. If you're worried that there are outliers in your data set, the median can be a particularly good way to avoid those problems when you're trying to make an estimator of the mean. Just to do another example, let's say you were trying to get a sense of how much power your wind turbine could be producing. Okay, so you were going to take a bunch of observations of the amount of power the wind turbine is producing on days. And you got days that are less windy and days that are more windy, but then one of the days in your sample happens to have, I drew it here as like a tornado. Okay, you're not going to run your wind turbine during a tornado, but you know what I'm saying. Like one of the days was just ridiculously windy compared to all the others. It was an outlier. Okay, that one day could drag the average fairly far. It could result in an average that doesn't actually represent the mean very well. On the other hand, something like the median would still be a fine statistic for estimating the mean under these conditions. I wanted to draw attention to the fact that your textbook actually does use a slightly different notation for what they mean when they write the median. They write that the median of a statistic is Q 0.5. Okay, this is an awkward notation. What they're doing is, in the textbook, they are emphasizing the fact that the median is the 50th percentile of the data set, hence the 0.5. And the Q actually stands for quantile. We'll get to what quantile means in just a little bit, but you can think of it as like percentile or something like that. So they're trying to show that when they use that notation, Q 0.5, that what they were trying to say is, see how it's the median is the 50th percentile. 50% of the observations are lower than this, and 50% of the observations are higher than this. That's neat, but it's not a very standard notation. I've never seen it actually outside of this textbook. So we'll be using this tilde notation when we're talking about the median. The average and the median then are two different ways that we can estimate. There are two different statistics that we can use to estimate the mean. Sometimes there's another statistic that you can use. Sometimes the mode of a data set can be an estimator of the mean as well. You probably learned about mode in like a math class in grade school or something like that. The mode of a data set is the most common observation in the data set. You took the temperature or you measured the wind speed a large number of times. What was the wind speed that you measured the most often? The mode of a random variable, the notation that we're going to use, is that the mode of random variable x will be MO of x, like MO little x like this, okay? Now, if we took our little example that we've been using in this lecture here, where we have these 13 or so observations of the temperature right now at different locations around the city, we could make a histogram, a graph that shows how often each of those observations occurred. And what we get is, okay, this one's a little weird because, I mean, we had that one outlier way out there at 47 degrees, and then no observations all the way up until, 74 or something like that, and then more observations up there. This is a mess. Let's not worry about the example that we have right there. Let me make a better example. Here's a histogram of some data. Let's say this is a large number of observations. This happens to be 125 observations. Let's say this is temperature in Omaha on 125 days of October 14th. Okay, the last 125 October 14ths in Omaha, we measured the temperature. And there were days where the temperature was as high as, what did I have there, 78 degrees. There were days where the temperature was as low as 48 degrees, and we have this distribution of them. And there is a mode. There is the observation that was most common. It happens to be 61 degrees Fahrenheit. Okay, again, I just made these data up on a spreadsheet. They're not real. And actually, if I took those 125 observations right there and computed their average, the average value of t bar, happens to be, what did I get? 60.984 degrees Fahrenheit. Holy smokes, my mode turned out to be a really good estimate of, well, at least a net good estimate of the average. and we know that the average is going to be a fine estimate of the mean. It may not be exactly the same as the mean, but it's a good estimate. Wow, that actually worked out surprisingly well. Modes are sometimes a good estimate of the mean. And they have certain properties that are really nice. Modes tend to be incredibly resistant, for example. Outliers have very little to do with what the mode is going to be. I mean, if I take a look at this distribution here, let's say I had an outlier. Let's say there was one day on October 14th, one year, I don't know, back in, let's say, 1962, where October 14th had a high temperature of 12 degrees. Okay, I have no idea why that would be. Would that change the mode at all? No, because it's out there in the tail of the distribution. That one time is not going to be the most common observation. It doesn't have anything to do with what the most common observation is. So, same with like if we had a day where October 12th, or October 14th, whatever we're saying, its high temperature was 97 degrees. Again, that wouldn't change the mode at all. Because no matter what, that weird outlier is not the most common observation. So, wow, that's pretty neat. The mode is a remarkably resistant property. It is not sensitive to adding or removing a few outlying observations. But that doesn't mean that mode doesn't have problems. There are problems with using the mode as an estimator of the mean that actually teaches us something important about medians and averages. I mean, there's no doubt about it. The mode is an incredibly resistant statistic. It is very, very immune to the problems of outliers. But, and here comes a vocabulary word, but the mode is actually in no way a robust estimator of the mean. It is not a very robust estimator of the mean. We need a definition, apparently, as to what we mean by robust. A statistic is said to be robust when it still functions as expected, even if the underlying assumptions about the original dataset prove to be untrue. Okay, let me get to that again here, just so that we're clear about what this, and then I'll show you some examples. A statistic, robust is a property, the robustness is a property of a statistic. A statistic is said to be robust when it still functions as expected, like it still is a good estimator of the mean or whatever, even if the underlying assumptions about the original data prove to be untrue. Okay, let me show you an example. Here's our data set again that happened to be 125, what did we decide this was? Measurements of the temperature in Omaha on October 14th over the last 125 years or whatever. And we found in this particular case that the mode was an excellent estimator of the mean, but it actually required certain assumptions that were sort of hidden in here. For example, we had to assume that the data were distributed in such a way that there was a hump. Okay, I mean, the hump being this mode, the place where there's the most. I mean, here, I made it, what if we had a uniformly distributed temperature distribution where every temperature bin from 48 to whatever I used here, 79 or whatever, had the same chance of being the temperature on that day. So like 5 of my years had a temperature of 48, 5 of the years had a temperature of 49. Okay, we had a very uniform temperature distribution. There is no mode. There's still an average. We could add up all these 125 observations and we get that the average temperature in those 125 years was 62.5 degrees Fahrenheit. There's still a mean. There is some mean temperature here. There just isn't a mode. And you know what? Let's say I took one more observation, okay? I have it exactly tied where there was exactly 5 observations of each temperature here. Okay, if I took one more, it'll break the tie, right? Ta-da! I took one more temperature observation. It happened to be 51 on my 126th year. And I get that the average temperature is 62, almost 62 and a half. And the mode, which is the one where there's the most, is a whopping 51 degrees. See how the mode had nothing to do with the average here? I mean, it's just the one, I mean, some bin, some interval on our histogram here had to be the most. On a uniform distribution, it could be anywhere. That any place in that range could have been the one where there was one more observation than the other ones. The mode had nothing to do with it. Okay, some random variables are distributed as a uniform distribution, and the mode doesn't mean anything in those kind of observations, much less is it an estimator of the mean. Another thing that you have to be assuming if you're going to be trying to make the mode be an estimator of the mean is you have to assume that the mode is somehow related to the mean. Now, that turns out not to be a terribly restrictive assumption, because in general, a lot of random variables are distributed in kind of a mound shape or a hump shape distribution. And in those cases, most of the time, it can be proven in a statistics class that the median and the mode should be the same. I'm sorry, the mean and the mode should be the same, or at least should be closely related to each other. Lots of random variables have that sort of bell curve type distribution where there's a cluster at the middle where most of the observations occur, and then tails. And as it turns out, the mode and the mean are typically related to each other, if not the same thing, in those kinds of distributions. And that's the kind of thing that makes a stats major sit up late at night proving for a homework set in a 500 level stats class. But for lots of other distributions, the mean and the mode are completely unrelated. I mean, like right here, I have an example of an exponential distribution. In this case, the lowest observation, 48, has the most times it was observed. The mode here is 48 degrees Fahrenheit. And then the number of times that we observed each of these other temperatures kind of tails off. It was less and less common the higher the temperature got. Well, there really is an average. The average happens to be 60.157 in this particular case. But what does that have to do with the mode? The mode is completely unrelated. The mode was just the lowest. Lots of processes in nature, lots of processes in engineering follow a exponential distribution where the most common observation is the smallest one, and then things tail off from there. The expected time interval between two decays of a radioactive atom, it follows an exponential distribution. The distance between knots of wood on a board follows distributions like this, and so on. The mode has nothing to do with the mean. The average distance the knots are apart has nothing to do with the most common time, the distance they are apart. There are lots of weird distributions out there. Here's a bimodal distribution where there are two humps to the data set, and I mean in this particular case the mode turned out to be 55, but that had really nothing to do with the average. The average was 59. If the average is an estimator of the mean, the mode is apparently not a very good one. See how this means, what this tells us about robust? The underlying assumptions that were hidden in here was that if you wanted to use the mode as an estimator of the mean, well, there's sort of a hidden assumption that there is a hump to the distribution, and that mode, the most common observation, is somehow related to the mean. If those assumptions weren't good, the mode is not a very good estimator of the mean. If the mode isn't a useful estimator of the mean, if the underlying assumptions, namely that the distribution has a hump, and that hump is related to the mean, if those assumptions aren't true, the mode is a terrible estimator then of the mean. In other words, we would say that the mode is not a very robust estimator of the mean. Okay? Just for contrast, on the other hand, the average is an extremely robust estimator of the mean. It might not be all that resistant, but it is very robust. So, like for example, I mean, no matter how weird the distribution of your data is, whether it's bell-shaped or bimodal or exponential or uniform or any of the other zillions of distributions that exist out there, no matter how weird the distribution of your data the distribution of your data is, the average turns out it can be proven to be always a reliable estimator of the mean. Wow, that's a nifty property. I mean, I often won't necessarily have any kind of idea in advance how my data is going to be distributed. I don't have a preconceived idea as to what the distribution will look like of the power coming off of a solar panel, or the power generated by a wind turbine, or the power needs of a factory or whatever. But no matter what that distribution is, it turns out average can be proven to be a reliable estimate. It is very robust. It's a very reliable estimator of the mean. Mode, not so much. Median, kind of in between. No pun intended. So it turns out average earns the fact, average is the statistic you know the most about, right? You've used it without even really thinking about it 100 different times in your life for different purposes. And average earns that respect because average has, while admittedly the disadvantage of not being particularly resistant to outliers, there's no doubt about it, average has the advantage of being extremely robust. In fact, X bar, our average, turns out to be something that every stats major, both loves and fears and dreads and needs and whatever else you want to say. It turns out, if you're trying to get a handle on the mean, this central tendency of your data set, it can be shown that the average is what stats professionals call the M-view. The average is the M-view. The M-view is the minimum variance unbiased estimator. Okay? For any kind of parameter you come up with, there should be some M-view, your best possible statistic for making an estimator of that. And it can be shown that for the mean, average is the M-view. It is the best you can hope for. It is the best way, based on a sample of data, to come up with an estimate of the mean. But you have to be aware of the fact that, like, it has this problem of not being very resistant to outliers. If you're worried about outliers, maybe median is a better answer. If you can have some faith that the data are hump-shaped in their distribution and that the hump is related to the mean and so on, then maybe mode will be a better answer. But overall, when in doubt, average is your best estimator of the mean, the central tendency of the data. Okay, before we leave this off, I want to ask you 2 questions and see if you can have a response. Suppose you were measuring the power output of a solar panel and you measured it, let's say, 10 times. You add up those 10 observations and you divide by 10. What you just computed was a blank known as the blank. Is that a parameter or a statistic, and is that the mean or is that the average? Okay, follow one of the 4 links below based on your answer and get some feedback, and then we'll move on to question 5.